All right, so to complete this neutralization reaction, yeah, what is the acid? Jade,
HCl.
what gave it away?
On the H.
And that means that the other substance is the base. Okay? Well, how do we make the salt? Anybody? Arshan?
You take the anion from the acid and the cation from the base.
You take the anion from the acid, which is chloride, and the cation from the base, which is sodium, and that is going to produce sodium chloride. That is salt. And then for the water, you just take hydrogen with hydroxide, and that is going to make H2O. What type of reaction is this? Is this synthesis reaction, decomposition reaction, combustion reaction, single replacement, or double replacement? Carson? This is known as a double replacement reaction. You learned this at the end of first semester. Neutralization reactions are double replacement reactions. All right. Let's get into a process known as acid-base titration. In chemistry, what? Down the hallway? Emma, can you take that door stop by the door so the door will close? So in chemistry, guys, there's a lab where you set up a device like this. And it's just basically a little pole. And it has a little arm. And in that arm, it holds a titration flask. It's not very symmetrical. And this flask is actually going into Erlenmeyer flask, which is this kind of half pyramid shaped beaker. And it's dripping an acid or a base into the compound or into the flask to try to neutralize it. So let's say this is an acid in here. What would I want in this long cylindrical flask to try to neutralize it? Would I want more of an acid? Would I want water? Or would I want a base? You would want a base in here. And I'm going to drop, literally, drop by drop by drop of the base until this acid is no longer an acid and it is considered neutral, which would be equal to water. I know that it's going to become an acid or go from acid to water when it turns a pink color because I have something called an indicator. An indicator is going to turn pink when the pH is elevated. But it goes back to being clear. I'm going to show you a video with all this. So I drop a little bit of the base in the acid, and temporarily there'll be a little bit of a bright, hot pink color, and then it'll go away. And then I drop a little droplet of base into it, and you can see a little bit of pink, but the pink goes away. You do this drop by drop by drop until, here's the end. When the pink no longer disappears, the solution is neutral, which is a pH of 7. This is known as a titration. I'm going to show you a video all about it. And it's basically taking the concentration of a known base and trying to find the concentration of the unknown concentration of an acid. So here's the definition for titration. A method for determining The concentration of a solution by reacting to known volume of that solution. So before I go any further, I want to highlight this part. A method for determining the concentration of a solution by reacting the known volume of that solution. So here's what we're going to say. What is another word for concentration? Do you recall? Molarity. So what you're saying is big M for molarity, you have no idea. But the volume, you do know. You do know how much there is, you just don't know the concentration is. So let's continue. You're going to do this with a solution of known concentration. So this can be a little tricky to understand at first. I'm going to try my best to really have you guys understand this. So I'm going to use visuals here to really try to convey this idea. You do not know the molarity, but you do know how much of it you have. So let's say, example 1, I have 5 liters of acid. I do not know its molarity. And what is another word for molarity? Concentration. Okay? So in this flask, this is called an Erlenmeyer flask. I have this acid in here. You know, acid is not really red. It's going to be clear. It's going to look like water. Don't drink it. This acid, I have 5 liters. So this means that my volume, V for volume, check. I know it. 5 liters. But for the molarity, I have no idea. So what I'm going to do is I'm going to pour this, oops. I'm going to pour this flask into a titration flask. And this titration flask has measurements on it. I will know how much, what the concentration is if I have a beaker down here with a base. And with this base, I do know the molarity and I do know the volume. All I'm trying to figure out is the concentration of this mystery acid. So this equation is actually M1 times V1 equals M2 times V2. How many variables are there?
4.
How many do you think you will be provided?
3.
There are 3. Yes, Nicole?
Would this not just get rid of the acid then?
You're going to neutralize it and trying to figure out what the how much acid did it take to make the base neutral. Then you're going to be able to figure out the concentration.
You would have the leftover acid.
Yes. Yeah.
If you know all 4, why can't you do the equation? Or if you know 3.
You can, but also here's the thing, Arshan. How much you're going to put the maximum volume in that titration, but you're not going to necessarily need all of it. So you will have to find out what volume was there because you won't necessarily use up all that volume. You'll see how this works out. I'm probably not phrasing it as best I could.
Oh, because you might not use all the volume.
That's right. All right, so I'm going to show you guys a video now. I'm going to pause the YouTube video. Before I do pause it, if you go on YouTube, you type in titration using phenolphthalein or phenolphthalein. This is the video I'm going to be showing in class. I can't really show a YouTube video in class. Copyright, copyright laws and all that crap. So I'm going to pause the video here. Yeah, the acid is in the burette. The base is down here. You can go either way. Like Arshan just asked on the video you just watched, the acid was in the flask, and the base was in the burette. You can go either way.
Alright. Does it matter which one is dropped into which?
No.
Like for none of it matter.
You just have to be sure that you know where your base is, you know where your acid is, where you put which one. Okay. So guys, in the video you just watched, here's what happened. The pH of the hydrochloric acid started at a pH of 2. Your y-axis is going to be the volume of base added. This is on the video that you just watched. And we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It just goes on and on. And so let's see if you can predict what this graph is going to be like. What's going to happen to the pH with every milliliter that is added to this acid? What will happen to the pH? It'll rise. And then all of a sudden, it gets a sharp increase. When it crosses that threshold of 7, a pH of 7, this is known as your equivalence point. This is when the hydrogen ions are equal to the hydroxide ions, and you have achieved a neutral solution. So just as I explained, the equivalence point is when the moles of hydrogen equal the moles of hydroxide. All right. Now that phenolphthalein that you just saw, that pink stuff, it was clear when it was in an acid. It was pink when it became a little basic or even neutral. This is how your parents' pool boy, or your parents yourself, some of you said your dad will maintain your pool. This is what they use to make sure the pH level is the proper range. Because when you put chlorine and bleach in a pool, it makes the water basic. You have to know it's at the proper pH level by putting an indicator in there. And when the indicator turns a specific color, that lets your parents know, okay, the pH of the pool is where it should be. So let's say that I had this little piece of paper. This piece of paper is an indicator. And if I dip this paper into pool water and it turns the piece of paper like, say, a lime green, I look at my key. Okay, what does lime green mean? It means a pH of 6. Okay, I need to make the pH of the pool 8. So I need to add more bleach. I need to add more chlorine. So I add more bleach, I add more chlorine, I let it circulate for maybe a day. I check the pH level, it turns yellow. So, okay, what does yellow mean? I look at my little key. Yellow means pH of 8. Perfect. The pH is where it should be. Good. That's how pool guys or your parents, that's how they maintain the pH level of the pool. This is due to acid-base indicators. These are instruments used to determine the pH level of any given substance. They can be chemical dyes, litmus paper, or others that change color when exposed to varying pH levels. Now, I'm going to have you guys do this in the lab. I totally, when I was telling you on Monday we're going to do a lab, I totally forgot that we didn't have class on Tuesday. But here's good news. Because there's no final exams, we're going to have 2 weeks of Nothing. We can do labs then. And I do want you to do this pH lab. And so what I would like to pull up here is the actual pH indicator I want to have you use. It's called pH tape. Let me see if I can find it here online. I'd have to order it, but I think we can get it. All right, so yeah, this is it. So here's how this lab is going to work. And you guys will, I do want you to do this in just a few weeks. So let's say Colby's group, turn off the light on them. Let's say Colby's group has a cup. And the cup has an unknown pH level. So they rip off a piece of little brown stuff, it's like tape, and they're going to dip it into this cup, and it's going to turn, like, say, a purple color. That means it's a pH of 8. Let's say it turns a yellow color, pH of about 5.5. There's many different types of pH tapes. Here's one that I'm commonly accustomed with. If it turns like hot pink, it's a pH of 0. Really dark blue, pH of 14. Let's say you get a pH of 7, that's going to be lime green. A pH of 5, orange. 2, dark orange. 9, kind of turquoise color. This is known as the pH indicator. On the lab I'm going to have you guys do, you are going to start off with a pH of, like, say, 13. You're going to find out how much vinegar it's going to take to get that pH of 13 to a pH of 7, which means vinegar is an acid. You're going to drop an acid into a cup of dissolved antacid, like Rolaids Alka-Seltzer. You're going to find out just which antacid is the best at resisting acids, like stomach acid or vinegar. But this is known as an acid-base indicator. You can hit the light. It's either a tape or some little droplet like phenolphthalein, or even a tool like a meter. You can stick a meter into the ground and find out what the pH is of the soil. Okay. So let's do an example, and I want to talk to you about acid rain, or buffers and then acid rain. So this should be your last math example. Have your calculators out. Actually still with us? All right. Everybody, the equation that you'll be using for this is M1 times V1, or excuse me, yeah, M1 V1 equals M2 times V2. Another way to look at this is the molarity of your acid times the volume of your acid equals the molarity of your base times the volume of your base. So you have 4 variables. You are given 3 in this problem. Let's see if you can identify which one is which. A volume of 18.28 milliliters of a standard solution of 0.1000 molar sodium hydroxide. Stop right there. Sodium hydroxide. Is that an acid or is that a base? Okay. Are you given the volume of that base? 18.28 milliliters. Are you given the molarity of that base? 0.1000 molar. Okay? What's required to neutralize 25 milliliters of a solution of methanolic acid? Are you given the volume of your acid? Are you given the molarity of your acid? Okay, so we have it understood. We have what we need to know. The molarity of your acid is unknown. The volume of your acid is 25.00 milliliters. Check. The molarity of your base, we are provided 0.1000 molar. Check. The volume of your base, we have 18.28 milliliters. Check. All right. Here we go. You must first determine the ratio of acid to base. In order to do this, guys, you need to write the neutralization reaction. So I would like you to do that. I provided you the chemical formulas, HCOOH and NaOH. Write the neutralization reaction. So our acid is HCOOH. Our base is NaOH. I need you to complete the equation like you did at the very beginning of class today. Now, there is a polyatomic ion here that you did not have to learn this year, so it might be a little confusing. So I'm going to try to help you out. This one is kind of tricky, so I think I'll help you out the whole way. So, guys, methanolic acid has methyl. A methyl group is HCOO. You know that a salt, over here you're going to have the salt, and you're going to have water. Now, you already know water is going to be H2O. That's easy. What part of sodium hydroxide makes it a base? Is it the Na or is it the OH? Okay, so this is the cation of the base. Now, I would help you with this because you have never seen this one before. This is an exception to the rule. This is obviously the acid right here. That's methanolic acid, but here's how it's a little different. H is part of the polyatomic ion. So this is the H that makes it acidic, not the one in front. I know that's a little confusing. I've been telling you all along the H is in the front. But here's what I'm getting at. Please listen. HCOO is a methyl group. This has a -1 charge. Sodium has a +1 charge. You put those together, you get, what is it? HCOONA. This is one of the very few examples where the cation is in the back, the anion is in the front. The reason they do that is because H is in the front of this polyatomic ion. So they don't want to make it HH. That just looks weird. You can't say H2 because those two hydrogens are separate from each other. So you're going to say HCOONA. Now, this equation is balanced. It's a 1:1:1:1 ratio. That's important. So the acid and base are 1:1. That's important to know. The next thing I think you can do on your own is convert the milliliters to liters. So please try to do that on your own. I think you can. You should know by now that there's 1,000 milliliters in 1 liter. So just shift the decimal 3 places. Let's see if you can figure out which direction. Yeah, but you need to put it in liters. We need to have a unit measurement for liters. So we have 18.28 milliliters. How many liters would that be? How many zeros are there in 1,000? Which way would you shift the decimal, left or right 3 places? Left. So it's going to be 0.01828 liters. And then we have 25.00 milliliters. That's going to be 0.02500. Okay. Now you can plug in your variables. So please go ahead and do that on your own. You have MB, VB, MA, VH. Just plug them in. You have 3 variables. Find the 4th. What was the molarity of the base? 0.1. The volume was 0.01828. Oops, that's liters. And then the volume of the other one is 0.02500 liters. Okay, I get my calculator here. 0.1 divided by 0.0128 divided by 0.025. Wait, I think I did something. 0.1 times 0.01828 divided by 0.025. There it is. The molarity of your acid is 0.07 molar. It's pretty much that simple. What would that be in scientific notation? 7.0 times 10 to the negative 2 molar, roughly. Yes?
So if the ratio to the acid and base would have been like 1 to 2.
You would have had to double it. You would have to double it. If it was 1 to 3, triple it. 1 to 4, quadruple it. If the ratio of acid to base was 1 to 2 or 1 to 3 or anything like that, you would have to double it or triple that number. Double the molarity or triple the molarity. So let's say it was a 1 to 2 ratio, for instance. That's 7.0 times 10 to the second. You would have to double it to 14.0. Because you have to neutralize all that acid or that base, because there'd be twice as much acid to base if it was 1 to 2 ratio. Half it. Yep, you would half it. All right. What time is it? We have 12 minutes. This is the last thing I have for you guys. And then tomorrow you can work on your reviews in class. Actually, second last thing is I do want to teach you about acid rain and ocean acidification too. Buffers. A buffer is able to resist the change to pH over a limited amount of time. These are solutions that resist changes in pH when limited amounts of acid and base are added. So buffers resist pH change. If I were to add an acid to a buffer, the buffer would not change to a point. To a point. This is going to be kind of a crude example here. Well, let's say our main man Max is a buffer. I'm not going to hit you, Max, okay? Relax. Max is wearing a red shirt, so he's an acid. I'm a base. And this calculator, put this on your head, all right? Balance that. Balance it. Balance it. That buffer, that calculator is a buffer. Now, normally, when I hit him, am I going to hit you? He's going to go, ah! But this buffer is going to resist that pain to a point. So if I hit him, nothing. Hit him, nothing. Hit him, nothing. Hit him, nothing. So what I'm doing, I'm trying, this is a horrible analogy, but I'm trying to work it. If you add a base to an acid with a buffer, normally what you saw in your video, see if you can answer this. It's bouncing. If I added a base to an acid over time, what would happen to the pH level of the acid? It would go up. Eventually go up and up and up and up. Here's what the buffer does. The buffer stops after happening to a point. So I'm adding the base, I'm adding the base, I'm adding the base, I'm adding the base, there's no change. To a point. Eventually the buffer wears out. And you will start to see changes in the pH. So buffers can resist pH changes to a point. And again, when I say to a point, that means that there's a limited amount of acid or base you can add until it does start to change. So it resists change to a point, but then it will change eventually. It's kind of like if you shot a gun at a bulletproof glass. Will the glass stop the bullet? Yes. What if you shot like 1,000,000 bullets at the glass? Would eventually a bullet make it through? Yeah. The glass can stop a bullet, but eventually it's going to give. So, you know, if Max is like, go ahead, hit me in the stomach, I can take it. Like, all right, you hear that? You feel that? No. So I just keep doing it. I do it, and I keep hitting him, and eventually it's like, okay, I'm done. He was acting like a buffer where he can resist that pain or he can resist that feeling, but eventually it gives out and it gives up. We have buffers in our body. There are buffers in aquariums that are supposed to maintain the pH level. When you start to try to manipulate pH, there's buffers in your pool. So we have buffers everywhere. It's just meant to try to avoid or prevent a change in pH over time. And the last thing I want to get to you guys today is acid rain. Okay. Acid rain is when pollution carrying nitrates, which is NO3 from cars, and sulfate, or no, sulfate or sulfite? Sulfate. This is from power plants. Goes into the atmosphere. And mixes with water in the clouds. So acid rain is a result of pollution, but it can also be a naturally occurring phenomenon because some of these same compounds come out of volcanoes. The planet Venus is one of the most hostile environments in our solar system because it has a runaway greenhouse effect. It is the second planet in the solar system, but it is the hottest planet because of its thick atmosphere. A lot of that atmosphere is due to the volcanoes that are on the surface of Venus. Those volcanoes spew out nitrogen gases and sulfuric gases, and it forms acid rain. And there's acid rain all over Venus. There's acid rain on Earth too, but more of the acid rain that we have is due to human pollution, not just natural stuff coming from the volcanoes. But this will form HNO3, which is nitric acid, and H2SO4, which is sulfuric acid. Now, let's see if you guys can tell me. When these pollutants mix with the water in the clouds to form rain, this is now technically acid rain. Now, when you hear acid rain, I don't want you to think of some Mortal Kombat fatality where you sprinkle acid on an enemy and you just totally dissolve into a pile of goo. It's not going to work like that. But by definition, if it is less than a pH of 7, what is it? It is an acid. So all life on Earth has been evolving for 4.6 billion years with water. And the types of life I want to focus on are trees. Trees and plants and grass are accustomed to a pH of 7. So we're going to call these plants, and they are accustomed to water, which is the pH of 7. What do you think happens to these trees when the rain falling from the sky is less than 7? It's basically like poisoning them. Acid rain lowers the pH of rainwater. So technically, it's acidic. This will go into the soil where trees get their water. And it basically toxifies the trees. And it can kill them. Also, when the rainwater falls from the sky, it can strip trees of their bark, not because the acid is really like burny chemical. It's poison because the trees are not used to such a low pH. And it can poison them, and it can actually kill them. It can strip trees of their leaves, it can strip trees of their bark, and it can actually kill the trees because in the roots underground, the roots are taking in this acidic water, and it can kill the actual plant. Yeah.
I heard it also these things called acid rain as well.
It can if it's powerful. So there's some medical conditions that have to do with acid, and I might have to take about 10 minutes from your review period tomorrow. Tomorrow, here's the 3 things I want to talk about. I want to talk about lactic acidosis, which is where your blood actually becomes acidic. I want to talk about alkalosis, which is when your blood becomes basic. And then I want to talk about ocean acidification. So I need someone, I know one of you has to be able to provide this one. Does anyone in here have access to a seashell? Just like a regular white bicarbonate seashell, anywhere. Not now, like when you go home tonight, bring it in tomorrow. Does anybody have a shell? Yes, like from the beach. Sure. Okay, bring me some shells tomorrow. I'll text you tonight, and we are going to demonstrate what ocean acidification is and how this is actually a big factor in climate change.